We are moving on today to logarithms, which is chapter 5. And I think that it's healthy to have an overall understanding of what logarithms is. So we'll talk a little bit about that. I was going to try to squeeze in 5.1 and 2 today. I tried doing that this morning. It didn't go so well, so we're going to slow it down. So lucky you, you get to benefit from what I learned in the morning, and then I apply that to your class. So this will go a lot smoother. So we'll just do a section per day, and that'll be the plan moving forward. And as a result, I've adapted or adjusted some of the things that were coming up. So your quiz will be on Monday instead of this Friday, which is nice. It'll give you a little bit of time. It's not meant to be a big deal. It's just a short little quiz with a few questions. And how about this, keeping in alignment with what I've been sort of doing, my adapted COVID version of teaching. The quiz is sort of like practice to get towards the test. I will mark it, I will count it for marks, but if you do better on the test, then I'll omit the quiz mark. Does that make sense? You'll be seeing some of the same stuff on the test. So I think it's reasonable that if you improve and you learn from the quiz and you do better on the test, then I'll just get rid of that quiz mark. Good? So you can view it truly as practice instead of this high stakes, high pressure thing that's causing you a whole lot of stress. Okay. Questions about any of that stuff before moving on? And then the chapter test is, I've pushed it to next Thursday instead, and that should allow us to ease our way through, learn things thoroughly and properly without it feeling way too panicked and rushed. Yeah, okay. So I think it's helpful to know what logarithms even are in the first place. It's the study of exponents. So this is what I mean. Like you will have learned exponent laws, I guess maybe for the first time it would have been in grade 9 perhaps. But even if you didn't, it's okay because we're now going to go through it and review it together. So a and b are positive real numbers, and x and y are also real numbers. We kind of don't even need to know that. That's just basically general talk about what we're working with. And let's just quickly review these. So we know from the past that if we have b to the power of 0, it's always going to be equal to 1. So basically, generally, anything to the power of 0, the answer is always 1. It doesn't matter how big and complicated I make the thing that I substitute in for b. I just know if the exponent is 0, the answer is 1. Good? These are all exponent laws that are in your workbook and in the notes I sent you, but if you want to copy them down as we're going through them one by one, it's totally your choice. But that's the first one. And the next one, b to the x times b to the y. So if we have the same base, then we can just add the exponents together. Good? I am just going to fly through them because I won't always do this, but I'm going to assume that you all know this. Is it safe to assume that? B to the x divided by b to the y, they have the same base again, so that means we can just simply subtract the exponents. Rule number 4, b to the x times y. In this case, we can simply multiply those variables together. Good? Number 5, we don't like to have negative exponents. So a rule that we learned way back is if we have b to the power of negative x, how to make that exponent positive is to take the reciprocal of the base. Remember that word reciprocal? So this is like saying b over 1. So reciprocal would be flipping it to find 1 over b. And then that exponent magically becomes positive when it's at the bottom. So just a friendly reminder. You know how this goes. I'm showing you the very basic simplified rules, and then we're going to build in other stuff that we've learned into this. But I think if you have a solid understanding of the basics, it's going to help us when we get to the harder stuff. Good? And this is kind of like the reverse of what we looked at a few examples ago. If we have ab to the power of x, then we can, I guess it's kind of like distributing. We can rewrite this without the brackets by saying a to the x times b to the x. I'm going to show you this over here, and I do not want you to write this down. This is a common thing that people, I'm sure in grade 12 or 11, you won't do this, but just a reminder, you are not allowed to do this because of that plus sign in between, right? What this means is a plus b to the x. So you would repeat it however many times that x is. It doesn't mean a to the x plus b to the x. We're all good with that, right? So that is definitely not allowed, but it's a common mistake that people are tempted to make, but you're not going to now that we've talked about it, right? And then number 7, I'm going to shrink this so we can compare to number 5. Do you see the similarities between number 5 and number 7? Number 7, we also would flip it and take the reciprocal, and we would also distribute the exponent to both parts of the variable, both parts of the fraction, sorry. So we end up with, we flip the a and the b, so it'd be b over a, and then the x exponent gets applied to both of them. Good? Questions so far? On to the last one that is in this dotted box for a couple of different reasons. We'll talk about them. I'm even putting a big pink star beside it because it's kind of a weird one, but you're going to see using examples why this is applicable or why this is important. A to the x equals a to the y if x is equal to y. It sort of is stating the obvious because we know an equation is like a scale. We've got to keep both sides balanced. So if this whole thing equals this whole thing, the bases are exactly the same number. So I could plug in there, like, it's up to you if you want to write this. If we have like 2 to the y, the bases are the same. So obviously for this equation to work out, x has to be equal to y. Otherwise this wouldn't be true. Does that make sense? So you might be wondering, I'm saying this because I was wondering, you might be wondering like why this is even a rule or why it's written there. So I'm going to show you with a few examples how this comes into play or why this is important. Good? Okay, so now having gone through that, I want to talk about, or just maybe very quickly show you something like this. Let's say I have 5 to the power of x minus 7 equals 5 cubed, for example. We're not going to solve this. You don't even have to write this down. I am going to show you other examples where we will solve it. But we've worked with lots of equations over the years. You've learned how to solve and isolate x to figure out what the answer is. But up until now, we've never had a variable that's up there in the exponent. The exponents, you can think of them as being needy. An exponent can never just hang out by itself, right? It has to be attached to a base. So it's not like I can just get rid of that 5 and the little x minus 7 can hang out by itself up top. That's just not an option, right? So that's why I say it's needy. And so it's because of this is an example where this rule comes into play. For this overall equation to make sense and be true, what has to be true, or what can I use to help me to solve this? Abtine? Yeah, so basically, like, you're technically not ever allowed to do this. You could never get rid of these 5s because that would leave the exponents hanging out by themselves. But we could just temporarily zoom in on the exponents and treat them as their own separate equation, applying this rule number 8. Does that make sense to everybody? And then I'm running out of room, so I'll write it up here. But if I have x minus 7 equals 3, this is what Abtine was saying. We want to get x by itself, so do you see that we would just add 7 to both sides? So then we end up getting x is equal to 10. I think I just told you we're not going to solve it, and then I went ahead and solved it. And I think I do this all the time. But anyways, does that help to clear up why rule number 8 is even a thing? That's how we apply it, or that's how it becomes relevant. Questions about that before we move on? Okay, so here's the next thing. So in some situations, we're not able to do that. Like if the bases aren't the same, would we have a method or a strategy for solving for x? As of right now, not really. So usually algebra is all about opposites. Like in this case here where I'm underlining, we know the way to get x by itself is to do the opposite, which is adding 7. But how can we do that if the x or the variable is up top in the exponent? This is what helps us to appreciate logarithms. Logarithms allow us to solve an equation that we've never been able to solve before, where we have a variable up top in the exponent. So that's what it is and what it has to do with. Logarithms are sort of like the opposite of exponents. Leah, can you do me a favor and just close the door? Thank you. Are there questions about that before we move on? Okay. Okay. This kind of looks like a nightmare. A little bit. It's not too bad, but kind of. So I don't know if you've picked up on this pattern, but what we do in every single chapter, every single function, every single unit is we take complicated things and we look for similarities and then we simplify and we break them down. Good? So this isn't equal to anything, but you can see that there's a lot going on there. It's asking us to simplify. I haven't taught you any strategies. We haven't gone through anything, but just based on past tools that you've picked up on, things that we've done in the past, can you think of an idea or a strategy to start to break this down? Gwyneth, is your hand up? Yeah.
Maybe you could like go 3 to the power of 2 for the 9 and 3 to the power of 3.
Excellent. So, everybody get what Gwyneth is saying? Basically, what Gwyneth has done is she's looked at the base at the top and the bottom, and she's looking at them in terms of similarities. Do you see how this is like a metaphor for life? Somebody needs to tell this to Trump. If you look for similarities and bring it to a common ground, we can start to break things down and make it easier. Does that make sense? So, thanks, Gwyneth. At the top, Gwyneth said to do 3 squared. I'm going to put it in brackets and I'm going to go really slow step by step so everyone's super clear on what we're doing here. I put the lines here to help me, but look how good of a job I've done of staying in the lines. I'll try to figure it out. At the bottom, how do we want to rewrite 27? Matt? Excellent. 3 to the power of 3. And then outside, we still have the other part that we haven't changed. But the reason we're allowed to do this is because, do you see technically we haven't actually changed anything? The stuff in the brackets are still the numbers that were written there as the bases. We've just written them in a different form, right? So then carrying on with this, I'm going to bring it down here. According to our exponent laws, this is why we reviewed them. This is what I'm teaching the grade 9s. I'm teaching them to live in denial. When there's a whole bunch of things happening here, let's just pretend the bottom's not even there. If we just had the top, what would the top simplify to? 3 to the power of... Sure, Matt? 24x, yep, and then we distribute this here, plus 6. Everybody good with that? Again, we're allowed to do this because I'm not actually changing this expression at all. I'm just writing it in a different form. As long as it still holds the same value, that's perfectly fine, according to the rules of mathematics. How about at the bottom? So by living in denial, I mean we just focus in on one part of it, focus in on the other part of it, then bring it back together, and then nothing feels difficult if you take that approach to it, the little step-by-step approach. So at the bottom, what do I end up getting? 3 to the power of, we can do, oh wow, that was crazy. Let's fix that. So we can distribute that there and there, and what do we end up getting? Thank you, 12x plus 3. So far, so good? So look how much better that's already looking. And then what would be the next smart way to deal with this? We can divide them top to bottom, so we'd have the same base. What do you do to the exponents when you're dividing something with the same base? We subtract them, and you're all going to be tempted to take shortcuts and do this, and I can't make you not do it, but I'm going to tell you that in all my years of teaching, the number of times I've seen such bright students who know their stuff mix up little things like forgetting to distribute the negative or just adding wrong. Like there's so much room to make little mistakes. The way to avoid that is take the extra 5 seconds to just write it out, right? Like write out this part and distribute it, and that'll eliminate, if you have a habit of like forgetting a negative or like adding something wrong and you find that happens, take the extra 5 seconds to just write it out and don't take shortcuts, and that should help to eliminate that. But basically, you don't have to write out every single little step, but I'm going to, so it's super clear. Do you see that we would actually get minus 12x minus 3 when we distribute the negative up top there? And then working our way through this, we collect our like terms there and there. And what do we actually end up getting when we clean this up? In the exponents. So we have 12x, right? Because we're doing 24x minus 12x. And then 6 minus 3. So it's going to be, so that's gone and that's gone. And that's what we end up simplifying to. So let's put this into perspective. Look again. This is what we were starting with. Isn't that amazing? So if we look for similarities and use our rules to start canceling things out and breaking it down, we end up getting this. And I'm going to take the box away for a second, and I'm going to say, or, is there another way that I could rewrite exactly the same thing? It would be fine if you gave me this, I would accept it, and that's correct. But is there another way that we could do that, or is there something we could do to simplify even further? Abteen, what would I do? Good. Everybody hear that? We can factor out a 3 at the top. So at the top, do you see that we would have 4x plus 1? And then a step further, what is this the same thing as? So we could actually say 27 to the 4x plus 1. And I mean, technically, they're the same thing. But if it does say simplify, we probably should simplify it as much as we possibly can. But there sometimes is debate over what people consider to be more simplified, because here we have a smaller base. So I don't know. I would accept either one. It's the same thing. Good? Questions? Not so bad so far? I mean, it kind of looks bad, but because we went through it step by step, taking that approach, hopefully it's not too bad. Okay, so we actually didn't solve anything. We just took an expression and we simplified it. And I'm going to ask you to solve this one. Based on what we just did, see if you can actually take it the extra step and solve this. So use the same approach. There's different ways of doing it. If you have a different approach, no problem. But see if you can simplify this and use your skills to find a solution. So we want to know what x is actually equal to. I'll give you a couple of minutes and then we will go through it together as usual. Yes. The last one? Yes, no problem. Good? Okay, so in this case, what's the common base that we would be looking at using? Matt? 2. Everybody good with that? So I'm going to rewrite this 2 to the 2, and then we still have the same exponent out there. Good? What's 32 the same thing as written in terms of 2? 2 to the 5, and then we still have that 1 minus x out there. So far, so good? Okay. And then distributing our exponents and rewriting this, we'd have 2 to the 6x minus 4. And over here, we'd have 2 to the, we want to distribute this, so it'd be 5. And here we'd have minus 5x. Everybody good with that so far? So here's where that rule number 8 comes into play. Technically, you can't really cancel out a base and just get rid of it, but we're using that rule or that idea to be able to work with what we have up top here. And so we could say we're kind of pretending that we're getting rid of it, but using that principle or that idea, if this is true, this equation, then 6x minus 4 must be equal to 5 minus 5x. Does that make sense? And the rest of this becomes just like the equations you've been solving since grade 9, and that is getting our like terms together and simplifying this. So we want to get these two together. Do you see I can just add 5x to both sides? So the hardest thing is keeping the color straight. So I don't know. I don't even know what I'm doing anymore. Oh well, it is what it is. So do you see that we would have 6x plus 5x, so we'd have 11x, and then 5 plus 4, so we'd have a 9 on the right. And we want x by itself, so we divide by 11. So x is equal to 9 over 11. Okay, that is kind of an ugly answer. Not to say that fractions are ugly, but you know, it makes things a little more complicated than we would like for them to be. But you can see the value or the importance of being able to solve this using algebra, because it's not easy to just look at that and come up with an answer of 9 over 11. Maybe it would be if we had an answer like 2, right? So these are the steps or the skills that we can use in order to look for the similarities, start to cancel things out, and break it down to find a solution. Does that make sense? So we haven't actually done any logarithms yet. All we've been doing is reviewing, which is what we always do at the start of a chapter. This is why you don't need to worry about missing out on anything or not learning the stuff you need to. This is us practicing exponents because that's what leads to logarithms. That's what it's based on. So I want to make sure that you're sort of back into that mode of thinking. And then once you're okay with this, I will introduce logarithms. So right now I'm going to get you to work on these questions.